In trying to keep these lessons short, sometimes I'll skim over an explanation. So if you have any questions, feel free to let me know. In the previous video, we looked at two rational functions. One of them was this. And after we determined that substitution leads to this indeterminate form, you saw me quickly identify one of the factors, in this case to be x plus 3 on the numerator. So when you have a rational expression, let's call it r of x, made up of polynomials, let's say p of x over q of x. And when using substitution, that leads to this indeterminate form. Then you can conclude that one of the common factors of both p of x and q of x is going to be x minus c. And if you want to know more about that, you can look up what's called the factor theorem. Now in this lesson, let's add to our toolkit on evaluating limits analytically. When you see an irrational expression like this, commonly they'll be like square roots, you can use a rationalizing technique. Well, first you're going to try direct substitution, and you're going to see this gives you another 0 over 0 indeterminate form. As we introduced in the previous lesson, let's say this is f of x. We want to find another function, g of x, that agree at all but one point. And in this case, that's going to be at x equals 0. So the rationalizing technique we'll use here is multiplying by the conjugate. What I mean by the conjugate is if you have a form x minus a, which is what this is, then multiplying by the conjugate is multiplying by x plus a. So let's multiply by the conjugate of the numerator. Just make sure whatever you're multiplying by is equal to 1, so you're not changing the value of the function. Now in the numerator, after applying the difference of squares, we get x plus 1 minus 1. These ones are going to eliminate each other, and we're just left with x on the top. In the denominator, we don't need to multiply this out, because we want that x factored out. So now we have our new g of x. And because these two functions agree at all but one point, which is at x equals 0, we can say the limit of g of x as x approaches 0 is the same as the limit of f of x as x approaches 0. And if it wasn't clear enough, the reason we did this is because now we can use direct substitution in the g. So let's do that now. 1 over the square root of 0 plus 1 plus 1. That's going to give you 1 over 2. And that function looks something like this. Well, this is the original f of x with that hole at x equals 0. And g of x looks the same, except that hole is filled. So we can confirm graphically as x approaches 0, y approaches 1/2. This time, let's also confirm our calculation numerically. As we approach 0 from the left, y approaches 1/2. And approaching 0 from the right, y also approaches 1/2. Which also confirms our calculations.